Right, Tawana. Let me talk about run length encoding. Run length encoding is a method of compression that is lossless. You still remember when we were talking about compression, we said there is lossless compression, there is lossy compression. Lossless compression being that compression method which can restore the file quality and all its data as compared to a lossless compression, as compared to lossy compression, which degrades the file for it to be stored in an efficient way, right? So in your syllabus, we simply have lossless compression um, method, which is called run length encoding. And this is the only one that you are going to do. We don't do many compression algorithms, although there are so many compression algorithms in the real world. But for you, you simply do one, which is run length encoding. So, if we talk about the reasons why we want to compress a file, you still remember we said we compress files in order for them to be easy to process, for them to be stored efficiently, for them to be sent on the network with ease. These are some of the reasons why we compress files, right? So to encode is to allocate bits or bit patterns to each character in letters. You still remember, if you go into your book, maybe we did not talk about it in detail. We were supposed to come back to it. I shall come back to it. When we said, when we are storing characters from A to Z using a SCII standard of encoding. The SCII standard of encoding says each letter has a fixed length of bits that are used to store it. Each letter in a SCII is going to have 8 bits or one word. So in the memory of a computer, each letter is a word or 8 bytes or 8 bits or 1 byte. You see what we're saying? Now, if we store files like that, it actually means we've stored files in their original form. To say, if we have 100 characters in a document, we have 100 by 8 bits, which is 800 bits. If we have got 10 characters on a page of a paper, it actually means we have 80 bits. This is called fixed length encoding. So to simply allocate bits to a file, to simply allocate bits to a character in a file is to encode. So why do we say a run length encoding is compression? It's because we encode by giving fewer bits per each character. If we change to say each file, instead of it being represented by 8 bits, we can now represent it using 4 bits. It actually means we are reducing the size of the file. We are compressing. This is a very simple method of compression where we are allocating fewer bits to a file that had larger bits by storing a very few bits per each occurrence, right? So take it to say to encode in this moment in time, to encode is to compress, to allocate fewer bits instead of 8. When we do that, per each character, to say each character no longer has 8 bits, but it now has fewer bits. When we use that method, we've already compressed the file. The file is already smaller, right? So this is what you shall see as we go here. Oh, my presentation is no longer moving there. What is happening? Oh. Yes. Yes, I've moved to the third slide there. Yes. Right. Look at the third slide there, where we are saying, assume that maybe we are having a document that has only 4 characters, A, E, R, and T. These are the only characters in our document, right? If we allocate 2 bits to each, it becomes 36 bits. Do you see that we've compressed the file there? Why? Because if we had allocated 8 bits to A, 8 bits to B, 8 bits to R, 8 bits to T, it actually means we'll be having, for A, we'll be having 8 bits, E 8 bits, R 8 bits, T 8 bits. It means we'll be having 32 bits. But look at what is happening there. If we opt to allocate 2 bits to each, to say A is 2 bits, that is 0, that is 00, E is now 01, R is now 10, and T is now 11. You can see that each character has been represented uniquely and properly. But instead of us having 2 bits, 32 bits for 4 characters, we now have 8 bits for those 4 characters. And we have already compressed the file in a very efficient way. And look at the sentence there. A rat ate a tart at a tea. This is the sentence that we've written. Under normal circumstances, that sentence was going to have 18 by 8 bits. It was going to have 18 by 8 bits. You can calculate that and see how many bits we'll be having. But now, instead, it is now having only 36 bits because we are saying each character is being represented by 2 bits. So for those 18 characters, instead of us having hundreds and hundreds of bits, each having 8 bits, we now have only 36 bits because we are saying each character is no longer being represented by 8 bits. Instead, it's being represented by 2 bits. Right? Let's go to the next slide so that you can see that with this kind of compression, we can even further compress the file. Hey, my slide is no longer moving there. Yes, we can even further compress the file. Look at what is happening there. Instead of us having 2 bits per each character, we have seen that A is occurring many number of times in that sentence. So therefore, for A, let us allocate 1 bit, which is 0. Then the number of occurrences for T, because we've said A is occurring the most, T occurs fairly many times. So T, we say T is now 10. Then R occurs fewer number of times. We now give 3 bits to R, which is now 110. Then E occurs very fewer number of times. We now give E 3 bits. Look, we are now using variable length encoding. We are saying the character that is occurring most should have the smallest number of bits. We are no longer following our actual fixed length encoding where we say each and every character should have 8 bits. Here we are now saying, because in this sentence only, A is occurring most, followed by a T, followed by R, followed by E. We are now saying R and E should have 3 bytes. Then A will be having 1 byte. Then E will be having 2 bytes. We've used the variable length encoding there. Now, if you read the sentence, a rat ate a tart at a tea, it can now be compressed to become 32 bits. You see, we are now coming to 32 bits. Why? Because we have allocated the most recurring letter A, we have allocated it 1 bit, and the least recurring letters, which is E and R, we have allocated them 3 bits. So by doing so, we are further compressing the file, right? So now, this is an example of lossless compression. We've said features of lossless compression are it checks for redundancy or recurrence of characters. Then it finds ways of reducing them, of representing them. Then it uses statistical methods to check the occurrence of characters or colors in images. It assigns few bits to most recurring characters and patterns. An example of such a compression is called run length encoding, which uses runs, right? So there we are with our run length encoding. Run length encoding analyzes the communication or the data file into successive arrangements of identical occurrences. It checks for frequent values and tells by replication count. It is used in situations where values are consecutively repeated, e.g., in images. A run is a series of the same character or color value occurring one after another, right? Run length works over the next, it works through tallying and counting the number of tallies, right? So look at an example. Don't worry about the definitions there. I've been running about them, but I want you to focus on the example there. Look, we have got a sentence which is A, B, 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 then we have a C, then we have 9 Ds there, right? So that sentence, look at what happens to the sentence if we represent it using base 10 numbers. A will be 97, B will be 98, C will be 99, D will be 100. This is how we can represent it, and we can convert those numbers to base 2, each being 8 bits, and we can still represent that data that way. Now look at the way we have compressed it. Below there, we are saying we have got 4 A's, we have got 6 B's, we have got 1 C, we have got 9 D's. There where we have a 5, we are supposed to have 9 D, we have 9 D's, right? So this is what we store. We do not store the D's themselves. We simply store the description to say we have 4 C's, we have 4 A's, we have 6 B's, we have 1 C, we have 9 D's. This is what we store. And then when we store that description, we are saying a series of A's that are occurring one after another is called a run. A series of B's that are occurring one after another is called a run. A single C there is a run. 9 D's are a run. So do you see that instead of us storing 4 A's, which is 32 bits, we are now storing 1 A and 1 4, which becomes 8 bits. We have stored its description, the description of the data, right? To make it easier, let us go to the next slide so that you can see clearly what I'm trying to say there. Oh, my slide is no longer moving again. Oh, my machine is slowing down. Yes, there. Look. We have stored 4 A's, 6 B's, 1 C's, 9 D. This is what we actually store and process. We store that on a computer. When we store that on a computer, when we want to retrieve, we then reproduce the whole sentence with repeating values. So we have summarized the occurrence of runs, and hence we now store each character and the count of that run on a file. And then it becomes very simple and easy to process. So what we are transmitting or storing is the description of runs. And when we want to present the file to a human being, we simply reproduce the runs through its description. And then the file begins to exist. So look, let us go to the next slide there where you can see a picture or an image being represented. Right? Look at the way we've represented an image there. Our F. F has been represented through, look, F is a matrix there. F is a matrix of pixels. But now look, we have stored the description of the pixels. When we have stored the description of the pixels, this is what we store and process each time we want the image. So when we are transmitting over the network or when we are storing, we are simply storing the description. But the description will help us reproduce the actual F. So 0 is representing a black, then 1 is representing white, right? So this is what we call run length encoding. A run is a series of the same characters that are occurring consecutively one after another. We simply take one character. When we take one character, We count the number of times the characters are occurring so that we store one character and the number of occurrences. So look at what happens. Do you see that if we want to store the word fruit, to compress the word fruit using run length encoding, the compressed file will be even larger than the uncompressed file. Why? Because we shall store to say there is one F, there is one R, there is one U, there is one I, there is one T. If we store that description, it becomes even bigger than the word fruit. This is why we say run length encoding is only useful where we have a large number of runs. Where we have very small number of runs, or where each character is occurring only once, it might not be possible for us to use run length encoding, right? So do you see that run length encoding is suitable for things like pictures, like videos, where we are saying the occurrence of a color value one after another is so high. Maybe we want to store 5,000 pixels of black. Then we can simply say black times 5,000. We store B, 1B, and the number 5,000. When we do that, it means we've actually used the 16 bits instead of us having 8 bits by 5,000 black pixels. This is how efficient it works. It works where there are runs. Where there are no runs, run length encoding cannot be used. And from the look of things, run length encoding can be used either as variable length encoding, it can also be used either as fixed length encoding, depending on what you feel is the best, right? So I believe you understand this. Try to understand it. If it becomes difficult, you can still ask questions. I'm available. I'll be doing this in the week so that we complete the first topic together. When we complete it, we get into our normal lessons as we had planned. So this whole week, I will have to finish all the bits and pieces of the first topic so that we get into another topic that we are planning to do. So for any question, you simply come back to our WhatsApp and then we can discuss. Thank you very much.